On? Yeah, great. Thank you. Left of the line. Good. So here are quickly just 2 slides from last time, and then I'll go back to writing just to review. So this diagram, left off an arrow, is the Chabauty diagram. X of q bets in a QP, J of q, QP, log map. In red, one thing we didn't state explicitly last time is this map is given fairly explicitly. The Lie algebra is, well, it's a tangent space. It's dual to the differentials. And the differentials on J, the pullback map gives you an isomorphism from differentials on J to differentials on X. And so this map has the description as it sends a divisor to, so we want a functional, so a map from differentials to QP. So it sends a differential to integrate that differential against D. And then for the black box version of Chabauty, the way I described it last time was, so there's the setup step, which is, well, just setting up p-adic integration. The top diagram, as Bjorn explained, essentially proves that there's some non-zero, in fact, dimension at least G minus R, subspace of differentials which annihilate rational points. So I think Jen called these annihilating differentials, or the annihilating subspace. And Chabauty's method, the coarsest version, can be described as there exists a non-trivial, in fact, this large, subspace of differentials which annihilate rational points. So here in the blue, we don't necessarily need P and Q to live in the same residue class. If they do, then this is a tiny integral, and we can compute this as if we're Calculus 1 students. And then it's fairly non-trivial. In a way, it's a form of analytic continuation to evaluate these integrals when P and Q live in different residue disks. So next time, I'll talk, or in the final 2 lectures, I'll talk more about larger integrals and analytic continuation. But for the analysis that I'll do today, we only ever have to compute tiny integrals. Okay, and then second slide from last time, so this is all just review, is that these integrals are locally analytic. I mean, there's a more precise version of that for us today. That simply means that on p-adic disks, we can compute these integrals via formal anti-differentiation. So to be more precise, if we have a point on the special fiber, so an FP point, and if we have 2 points in the tube, so this tube is the residue disk, so it's the set of points which reduce to P mod the prime P. This is analytically, so this isomorphism is given by p-adic power series. We saw an example of this last time with a hyperelliptic curve where you have to take a square root. So analytically, and this send, if we pick a uniformizer T at P, or really at some lift of P, then this map is given by send a point to evaluate it at the uniformizer. And then these integrals, also one point is that these integrals are functorial. In a sense, the inverse of this isomorphism is mapping a disk into your, well, rigid space, but in the QP points of X. And so when you pull back, you get an integral on a disk. So restricting omega to a disk, I mean, this is, okay, a p-adic disk is totally disconnected. It's not really a disk. Coleman told me that Dwork liked to call the boundary the p-adic unit tire rather than circle because it's open and closed. Nonetheless, there are certain ways in which it behaves like a disk. For instance, the de Rham cohomology of a disk is trivial, and so a differential on a disk is exact. And again, that's actually a theorem of Coleman, so a calculation, or some more general theorem of Coleman. So if you restrict omega to this disk, it has a power series expansion. Had a few questions after last talk about why the coefficients are in ZP. I mean, the short, vague answer is essentially that you're doing everything integrally over spec of ZP, and you can kind of deduce it from that. But this is a really important fact when we start doing an analysis. And then when you integrate, you introduce denominators. The coefficients are now in QP, but so this integral, which I've named I of t, or if I'm more careful, I omega t. So it's a power series in t. It has QP coefficients, but its derivative has coefficients in ZP. And when we do the Newton polygon analysis in a second, that's what's important. And again, so when we talk about analytically continuing, then we'll need to use calculus 3, but for now we just use calculus 1, fundamental theorem. And then what I want to talk about now is a short proof of Coleman's theorem, and then we'll work on generalizing this and introducing some new tools to help with that. So Coleman's theorem from effective Chabauty, although now there's a question about what effective would mean. These days, I think effective should mean you have an algorithm to compute. But so Coleman's theorem, as we discussed, is not an algorithm. Still, effective Chabauty, it's an upper bound on the rational points. Or rather, he took Chabauty's method and explicitly analyzed the zeros of these functions. And the output is, if you have a nice curve, rank less than genus, P a good prime, and I left off a hypothesis. I want P at least 2G. So before we had 2R plus 2. If R is at most G minus 1, 2R plus 2 is at most 2G. Okay, so this is slightly coarser, and we get this found. So let's prove that. So first slide. Yep, I want to write this. I don't want to cheat. Okay, so proof. First I'll draw a picture. So this one's genus 2. We have the FP fiber and the QP fiber. And if you have a rational point or a QP point, it reduces to an FP point. And of course, the special fiber only has finitely many FP points. So the first step is to break our analysis into residue classes. So let Q be a point in X of FP. Again, so step 1 is to calculate an upper bound on the number of rational points which reduce to a fixed Q, and then to sum that bound over all of the FP points of X. Great, so let this in Q, and then fix an annihilating differential. Some more notation. Let n sub Q be, all right, so let's leave some room. So I'm going to take omega, and I'm going to take its divisor. Well, omega is holomorphic, so I'm just taking its zeros with multiplicity. And I'm going to look at the zeros which live in, okay, I only picked one lift, but really you get a residue disk. You get a collection of points which map here. So Q, and then the tube or residue disk. So look at the zeros which live in the residue disk of Q, and then count them. So this is still a divisor on that. I'll take the degree. And then the claim, so we'll do a second proof to prove this claim. Then the number of zeros, so the number of Z in PZP, such that the integral of omega is 0. Okay, so this quantity is, let's see over here, this quantity is, we're counting the number of zeros of this. So remember, any pair of rational points in this residue disk is going to give you a T1 and T2 such that this vanishes. So our goal is to bound zeros of this. And Coleman's calculation is that, again, given this assumption on P, this is at most 1 plus NQ. So let me star this. We'll defer the proof for about a slide. But this is, in a sense, a p-adic-Rawls theorem. So we're relating the derivative of I is omega. So we're saying that a function has, at most, one more zero than its derivative. Also, I swept this under the rug, but here's a funny point. I won't write this. I'll just gesture enthusiastically at it. When we do this analysis, so we work point by point on the special fiber, when I'm writing out this integral, really, I'm fixing a base point. There was some discussion during Jen's talk about constants of integration and so on, but since I'm only working residue disk by residue disk, I actually want to pick a separate, if I can, a separate base point for each residue disk so that I only ever need to do tiny integrals, so that I only ever need to do calculus. And here's a point. So if all I want is an upper bound, then I'm going to concede a 1. Here's what I mean. Either there is a rational point in this residue disk, in which case then I pick it and use it for my T1, or there are no rational points in this residue disk. So great, if there are no rational points in this residue disk, then there's nothing to prove. 0 is less than 1 plus whatever positive integer. Okay, so anyway, subtle, or not subtle point, just point. And then Coleman's theorem is actually completely, I need more space, so completely direct from this. So if you believe this bound, we'll prove that next. Then the number of rational points of x is at most, okay, well, I'll throw this in, the number of rational points of x, QP1. So this is from Jen's notation. This is just the QP points, the QP solutions to these integrals. By the green star, this is at most. So we sum over Q on the special fiber, so the reduction. And then for each Q, we get at most 1 plus NQ zeros of these integrals. Now remember, every rational point in a residue disk appears as a 0. There might be, I can explain in a second, there might be other zeros of this integral. There might be transcendental zeros, and then sometimes there are zeros coming from torsion points, meaning torsion points from the Jacobian, which intersect the curve defined over a finite extension. Those are easy to deal with. The transcendental ones are less easy. But on the other hand, we can break this sum into 2 parts. This is sum of 1. Okay, so I'll go first. This one is of Q, F, Q. So this part is just size of X, FQ. And then this part, so these are the zeros of the differential omega, or rather its reduction to the special fiber. And so this is at most 2G minus 2 by Riemann-Roch. So this is the degree of omega. So we're using Riemann-Roch. Let me just comment. Already, one place where you can improve this bound is omega might have zeros that are defined over some finite non-trivial extension of FP. And since we're only looking at rational points, those zeros do not appear here. So let me restate that. If omega has zeros which are not FP rational, and then already this bound is not sharp. Jackson.
FP and FQ.
That's a P. No, you're right. The nice thing about a lowercase q is I can't confuse it with my capital P's. Okay, great. So that's the proof of Coleman's theorem modulo this. And I think the template is kind of nice. So again, you're working residue disk by residue disk. Actually, one comment on effectivity, I'll slide this back over, is I said before, there might be some q for which there's no rational point in its residue disk. So if you want to improve this bound, or in magma get exactly the right number, you need some technique, some local technique to, if there are no rational points in this residue disk, then to prove that. Now, of course, when I say local, this is smooth. So there are going to be QP points which reduce to this. So there's this weird technique called the Mordell-Evasive where you have to you kind of use information at different primes, even though you're looking in a QP disk. Yeah. Oh, great, thank you. So this subscript 1, this is the first Chabauty set. So these are the QP points which vanish under the abelian integral. If you like, just ignore that. And then quadratic Chabauty will fit some subscript 2 set, and then really there's kind of a filtration. But again, I should also point out that we didn't really compute an upper bound on x of q. We computed an upper bound on this. And this might be strictly larger. Well, in general, this will be strictly larger than that. Great. So where do bounds come from? How do we prove this? Okay, so let's phrase this as a lemma just about power series. So let f of t be a QP power series. It's raining. Such that its derivative, this is fairly special, but it's the situation that we're in. And I didn't leave enough room. We'll let this be ai t to the I, and then this will be I plus 1. Okay, great. So this is the integral. This is the f that we started with on this slide. And then let m be the order, so I'll explain, t equals 0 of the derivative mod p. So by order at t equals 0, I mean it's the first non-zero power of t that appears. The way you should think about this is, in general, this f prime, the coefficients are going to be non-zero, but maybe they're 0 mod p. Since this f prime corresponds to this differential, I'll just say note that m is this in Q in our previous proof. So if this was the differential, then you're picking up the zeros of the differential mod p. And additionally, suppose that m is at most p minus 2. And I'll just say, okay, so this is the same as saying p is at least m plus 2, and then note that m is at most 2g minus 2 by Riemann Roch, using the green comment. So in particular, this is where, okay, we'll see where this comes out in the proof. This is where the hypothesis that p is at least 2g comes from. So here it looks like you can get by with maybe 2g minus 1. Then the conclusion is that f has at most m plus 1 zeros in p zp. So I've just restated without the Chabauty setup the lemma about power series that we need here. And a comment really crucial is that we're only looking at zeros in p zp. And so that's because, back to our locally analytic slide, this isomorphism really is with p zp. For this uniformizer, if you have some q which reduces to p, I mean, it's going to be congruent to 0 mod p. So actually, so if I wanted, I could say proof Newton. So I'm giving a slide talk, I would put a box here. But let's explain. So the proof is you write out the Newton polygon of f and analyze it. It's a pretty calculation. Okay, so Newton polygons. So how does this work? And then I already know that I care about m plus 1. And okay, let me draw it first, and then I'll. So you plot I, and then it's f, not the derivative. So we want the valuation, so the p-adic valuation of a I over I plus 1. And I off by 1 here. So I want, great. Then you take the lower convex hull. So first, note that V of AM is 0. That's the definition of M. It's the first power of T for which the coefficient of T is non-zero mod P. Okay, great. And then because of our bound on P, so Min-Yong asked during my last lecture, where do these come up? Here's one of the two places it comes up in the analysis. The valuation of this denominator is 0 as well, because we forced it to be 0. P is greater than m plus 1. So in particular, when we draw the Newton polygon, we get one piece of information for free, although we've set up our hypotheses this way. Next, the valuations of the AIs are positive for I less than m, and the valuation of I plus 1 is 0. Okay, this part for the same reason. And here, again, it's by the definition of m. All of the coefficients of f prime, so these AIs, vanish mod p up to but not including m. So when we draw the Newton polygon, you get some scatter plot, and you have no control. But then this is a power series, so it could be bad to the right. But here's the point. The valuation of AI over I plus 1 is at least, so the valuation of AI is either 0 or positive. It's never negative. And then the valuation of I plus 1, like the p-adic valuation, that grows slowly, so logarithmically. So this is at least, so you can work out as an exercise, VP of I, okay, that part's plus 1. I start over, minus plus 1, and this is at least m plus 1 minus, so just short calculation. So in particular, when you draw the Newton polygon here, these might be negative. You might have denominators divisible by p. But the slopes can't be too large. So in this area, you have no slopes which are less than or equal to -1. And so I claim that actually does complete the proof. So remember how Newton polygons work. If you have a slope of, if you have a segment of slope alpha, then that corresponds to your function having roots of valuation negative alpha. So all of the zeros come from this chamber, and here's its length. There's the m plus 1, as promised. And then nothing to the right of m plus 1 contributes any zeros to f. So a couple comments. Again, if you're working in magma or by hand, you don't need some coarse argument that works for every curve. You can just write out your particular power series to whatever t-adic and p-adic precision you like, and then draw the Newton polygon. And after some finite calculation, you get usually a much better bound than this m plus 1. And of course, this is something that's easy to automate in magma. So if p is less than m plus 2, there might be some range where you get a few more zeros, but it's not that difficult to do the analysis directly. And lots of authors have written down explicit functions that add an error term to this. Great. So in the later lectures, so I joked last time, but it's not really a joke, that tropical geometry is like Newton polygons on steroids. And so one thing tropical geometry gives you is better analytic tools like this to analyze zeros of functions in power series, or better, the place where it's most powerful is if you have something like symmetric powers where you have, or surfaces where you have multiple integrals and multiple variables. And so instead of a polygon, you get some polytope. You have to do, it's called tropical intersection theory.
Can you say again what the property of Newton polygons is that tells you it has that most equals 1, 0?
Yeah, it's just that slopes, let me try again, slopes. Oh, great, thank you. Aaron asks if I could repeat the property of Newton polygons that lets me put the black box here, that does this analysis, and it's just that slopes, or sorry, segments, nope, of slope alpha correspond to roots with valuation negative alpha. And so if I want a root in PZP, I would need a corresponding slope with valuation a negative integer, because the valuation of something in PZP is a positive integer. So great. So I hope that's clear. And then the length of the slope, sorry, the length of the segment corresponds to the number of roots. Great. As one other quick pitch for more classical tropical geometry, how does it generalize Newton polygons? Well, one time. Well, let's say 5 briefly. In general, if X is a, say, over QP, or really over any valued field, a variety, then trop of X you define as, you can take X of QP, you can take the valuation, and you take maybe the closure. So what I mean by this is, okay, actually, I don't want a variety, I want an embedded variety. Maybe it's a subvariety of affine space or GM. I take the valuations of the coordinates of all of the points, and then take the closures. So here, the variety is defined by a single polynomial, or there's an analytic version, maybe a power series. And what we're trying to compute with the Newton polygon is the valuations of roots of that polynomial. So in higher dimensions, well, there's infinitely many roots, you're still computing the valuations of the solutions to some equation, or equations. And the point of tropical geometry is that there are interesting tools like Newton polygons, which help you. So as an example, if you take x plus y equals 1, then the tropical variety looks like the picture you see when people give, it's a tropical line, when they give talks like this. And the point is, look, if x is divisible by p, y cannot be divisible by p. So you kind of get this ray. So these continue. If y is divisible by p, x is not. So you get this ray. And then there might be denominators. We're really looking at QP solutions. So if x has a denominator of some power of p, y has to have the same power of p in its denominator. So you get this ray as well. And then if I were to only plot the, so really I lied, I should put closure. If I were to only plot the QP, or the valuations of QP points, you would get a discrete set. For QP bar, you get something that's at least dense in this, then either you take the closure or work with CP. And what's neat about tropical geometry is that you can relate the picture you get that I just drew to what the degeneration of this looks like. So if I take, I like to use this example. This one's projective, so what I write won't be completely literally true. If I take something like this elliptic curve, mod p, this is in P2, you have the intersection of 3 lines. So this has, non-trivial pi 1 as a graph. And then the tropical, so there's non-trivial Betti number, and then the tropical variety looks like some funny hexagon, but then with, I'll get the angles wrong, but with something coming out. It's not a fractal like the Berkovich spaces we'll draw later, but the point is the monodromy you get in this picture is the same size as the monodromy you get here. So Newton polygons, but in higher dimensions. Okay, so wait, we started at 10:08. Okay, so I want to finish at 10:58. This one? This is a bad rendition of the collection of p-adic valuations of roots. Really, I'm taking the affine piece. But in general, the picture you get when you draw trop of x, at least if you pick a nice enough embedding, has the same homotopy type as this picture. Or by homotopy type, I really mean you should take the dual graph and take the homotopy type of that. So for instance, if I take an elliptic curve with good reduction and take trop, it'll be more complicated than this, but it'll be contractible. Or if I take a conic, it won't just be a line, but it'll be contractible. Okay, great. So I want to improve Coleman's theorem. Let's talk about the proof of Stoll's theorem. So here, the idea of Stoll's rank favorable improvement is, look, we only used one differential in this argument. We actually have a often 2 or greater dimensional space of differentials that we can use in Chabauty's method. As long as we're doing a residue disk by residue disk analysis, let's at least pick the differential which gives you the best upper bound in each residue disk. So let me say that more precisely. So Stoll's idea is to pick the best for each. So define, now I'll introduce a W, and this will be the NQ from before. Now I realize. Okay, I won't comment on it until someone notices. So again, we take the zeros of omega in the residue class Q and take its degree, and then let NQ. So I'm redefining NQ. The minimum of NQ for W and V, where V is this space of annihilating differentials. So if V has dimension 1, we've done nothing. But in general, if you have 2 independent differentials, one of them is likely, in fact, certainly if you think about Riemann-Roch, we'll have, well, okay, anyway, one of them is likely to have less zeros in your given residue disk than another. I mean, of course, they each have 2G minus 2 zeros over the curve, over the algebraic closure. But you expect to get some savings. And then the same analysis from Coleman's proof tells us that XQ, or if you like, QP subscript 1 in Q, so we go disk by disk. It's an FP. And so this is still, at most, we sum the ones first. And then again, this is bounded above by 2G minus 2 from Riemann-Roch, but we can do better. And so Stoll introduced just the right amount of formalism. So let's turn this sum into, yes?
Why should that sum still be bounded by 2g
Yeah, so Zev asks, why should this sum still be bounded by 2g minus 2 if we're varying omega? Well, how about, let me put this here. How about this? This sum of nq is still at most sum of nq omega for some fixed omega, because these are minimums. And then this part's bounded by 2g minus 2, because it's a fixed omega. So I hope that's clear. Or to put it another way, for each residue disk, yeah, you're hopefully getting something smaller than you're bound before on each disk. Okay, great. So Stoll introduced the following formalism. Let D, in some of our papers we write D sub chub for the Chabauty divisor, be, let's just make this a divisor, NQ Q, X of FP, and then claim is that, well, okay, and then the degree of this is the quantity that we're trying to bound. Claim is that the degree of D is at most 2R. Let me recall again where the rank comes from, the dimension of V. And V is where we pull these omegas from when we set up in Q, is at least G minus R. And then his observation is that D is special. So everybody's read chapter 4 of Hartshorne. What does special mean? So if K is a canonical divisor, then, okay, well, the definition is D is special. Maybe I want effective here, so greater than or equal to 0. Special if, okay, well, the quick way is the dimension of this is at least 1. But this is equivalent to say that there's some canonical divisor K prime, which contains D in its support. So again, a divisor is special if it appears as part of the support of a canonical divisor, an effective canonical divisor. Or equivalently, if you prefer line bundles, the proofs are cleaner that way. This is just equivalent to say that the dimension of this is positive. So these are just differentials, but where you impose vanishing conditions at D. So here, an omega, or a non-zero omega, is an element if and only if div of omega contains as a subdivisor D. So it's just a rephrasing. And then Clifford's theorem is that if D is special, then let's try it again. The degree of D is at most, why am I blinking? Is at most, I got this backwards. The dimension, that's why I hesitated. The dimension of H naught of XD, so the linear system, is at most the degree of D over 2 plus 1. So quick context. is simply that, okay, so Riemann-Roch tells you, I'll use the standard notation for divisor D, this duality is degree of D plus 1 minus G. And so if the degree of D is very large, then this is 0, H naught of D is linear in D, and you have an exact formula. This tells you that if the degree of D is very small, so small enough that the H naught of K minus D might contribute, and of course this contributes if and only if D is special, then this gives you actually some extra savings, so some additional information about X naught of D. It's much smaller than this would predict. And then this lowercase h means the dimension. Okay, so great. Let's finish Stoll's proof. Great. So, poof. It's cleaner if we use line bundles. So if we look at, remember this, okay, if we call this D is now in Q, then if I look at H naught of X mod P, and I take omega 1 and twist by minus D. So I really thought I would have more room. As I said here, an omega is an element of this if and only if that omega has zeros at the support of D. So to put this another way, every annihilating differential, because of our definition of Q, is an element of this set. Let me explain this backwards, which is we cooked up D so that these NQs are the minimum order of a 0 as we range over V. So every element of V has a 0 of order at least in Q, at Q. That's exactly what this space is. Okay, and then on the other hand, so this tells us that G minus R, okay, this is the dimension of V, is at most the dimension of H naught of, I'll just say, omega 1. Okay, on the other hand, Clifford's theorem tells us this is at most 1/2. Okay, the degree of this is 2G minus 2, and the degree of this is our desired quantity. So this is 2G minus 2 minus the degree of D plus 1. And then check it out. This G cancels with this G. This cancels with this. And if you collect, you get that the degree of D is at most 2R. Where? Great, perfect. I agree. Thanks. Nice. At least I had the correct number. Okay, great. So when I talk about the black box version of Chabauty, I like to break it up into setup, so the integration theory part, local analysis, the fact that these NQs bound the number of zeros of integrals, and then some kind of global coordination before we used Riemann-Roch, so a theorem from geometry of curves. Here we're using Clifford's theorem, a theorem from the geometry of curves. And I'm using that P, yes. Thank you, Tony. Tony asked, I'm using a prime of good reduction. So I was maintaining the hypotheses from Coleman's theorem. So the way that I got into tropical geometry is the following, and then I'll explain the discrete version of tropical geometry, which is chip firing, and then the full, powerful version using Berkovich spaces over the next 2 lectures. But which is the following. XFP is a smooth curve. That was our hypothesis. And in Hartshorne's book, Clifford's theorem only works for a smooth curve. So when I was in graduate school, when I was trying to take the fiber product of various theorems, I was trying to generalize this argument to the bad reduction case. And I was able to prove that if you have a reducible curve, so multiple components, Clifford's theorem still holds. And then this argument works, or so I thought. So I submitted a paper, the first paper I submitted, and after it had been in review for about 3 months, I was sitting in a talk, and Caparasso gave this interesting example of a degeneration, and it bothered me, and I thought about it for a while and realized that it contradicted my argument from my paper, and talked to her about it. And of course, she was correct, and I had to withdraw the paper. And the error is essentially that the notion of special is not good. I'll say what I mean for singular curves, or at least reducible singular curves. Just as a hint of what the problem is, these spaces H naught of D still exist, but the problem is if you have some F in here, maybe F vanishes identically here and has some 0 here, or vanishes identically here and has some zero here. So basically, it's very rare that a divisor on a singular reducible curve is special in the traditional sense. In fact, K, the canonical divisor, is often not special, which is a bad sign. What I mean is there exist degenerate curves such that, and so what I mean here is these are P1s and they meet in this kind of cartoon, such that there does not exist an effective canonical divisor. Which is to say, how do you define the canonical divisor? You take a section of omega, so you take a differential, possibly, if you can, holomorphic, but in general, maybe it has some poles. Like when you compute the canonical divisor of P1, you take dx, which has poles. And so on something like this, it's possible that every canonical divisor vanishes along some component. And so when you take div of it, you don't get an honest-to-goodness divisor. And what I'll say finally, so I have 2 minutes, is so there's an institute in Barbados run by McGill where they have a mathematics conference once every, or twice a year. And for the number theory conference, they pick someone awesome. So Mignon did this once. And then the year I went, Matt Baker was selected, and they had Matt give 10 hours of lectures about tropical geometry, and then handpick 10 other people to give 1 hour of lectures just to teach us how things worked. So I got to learn tropical geometry in Barbados, and I kind of got to know Eric Katz there. And afterwards, he was very good at having ideas, and we kind of figured out that that you can fix this by throwing away the curve and just working with the dual graph of this curve. So the discrete version, I'm out of time. The discrete version of tropical geometry is to replace, so the dual graph would be for each component, you put a vertex, you connect them if they're incident, and then there's a notion of divisor on the graph. So if I had some divisor like this, it would specialize. I would put a 1 here, a 1 here, and then zeros. And so next time, I'll spend about half the time, I hope, talking about this, which I think of as the discrete version of tropical geometry, and how this fixes our problem here. And then we'll move to the continuous version. So, thank you.
Questions?
Is it easy to see why the Chabauty divisor from Stoll's method is special?
Yeah, actually. That's a good question. So, wait, where did I put it? Here. Yes, so special is the same as saying that. So I claim it's actually by the definition of these n sub q's. So if you prefer differentials, D is special if there exists a differential which has zeros at D. Okay, but this D, we did this backwards. This D, for all of the differentials we're considering, in fact, this D, so A, it follows from this, but B, we contrived it that way. Every differential has a zero of order at least in sub q at D. That's what D is.
Hi. I was wondering if there's some point in the tropicalization procedure if you want to pass from, say, from QP to QP bar or CP.
Right, so for the discrete version, no. That makes things complicated. I think, as you know, as you increase the ramification, you have to subdivide these dual graphs. And that's a problem, but this is what Berkovich spaces solve. Instead of working with the discrete graph, you work with a metric graph. And when you subdivide, it's already subdivided. So when you pass to some extension of QP or CP in the Berkovich setting, I mean, it's a feature, not a bug. That helps you. Whereas here, it makes it more complicated. And we do want to do that. So for instance, it's better to work with semi-stable models. There's a bounded degree extension over which you have a semi-stable model. So we really do want to extend the base.
So in Stoll's theorem, you're using this improvement that you're picking the best omega for every residue class, but you're still not considering all the omegas at once. So you're still not intersecting the zeros of all the omegas. Is there a way to make that work and get something better?
I mean, I've tried to do that, not that I know of. Yeah. Or at least not using the discrete techniques, so-Newton polygons.
Okay, thanks.
All right, so maybe in the interest of time, let's have one last question and then take a break.
The not that you know of, you just said, that means in the general case or in specific cases?
In the general case.
Okay.
Yeah, I'll say that.
Okay, let's thank David again and take a half-hour break.